Hello friends, welcome you all this video lecture of electronic science. In this lecture, we shall study the state equivalence and state reduction method. Myself, G.G.Patil, Department of Electronic Science, KTHM College, Nasik. So let us start. In this lecture, we have to study the importance of state reduction in sequential machines. What is the advantages of state reduction in sequential machine that we have to study? The designer usually constructs the state diagram from a written or verbal problem statement. Once an initial state machine diagram is constructed, the redundant states can be eliminated, identified and eliminated. Now, what is meant by equivalent state, or when we can say the two states are equivalent? That is given here. The one state is equivalent to another and therefore said to be redundant state if the state functions are indistinguishable. If the state functions are indistinguishable, then and then the two states are said to be equivalent states. What are the advantages of state reduction in implementation of sequential state machine? There are a number of advantages of reducing the states in state machine which are listed here. The number of state required to realize a sequential machine directly affects the cost of sequential circuit, operating speed of sequential circuit, and complexity of sequential circuit. And due to these three factors, the state reduction of equivalent states is important in implementation of a sequential state machine. If the number of states are more, then to implement such a large number of state sequential machine, it requires more component. So the circuit cost increases as the number of cost increases. Since the number of components are more, it has each component has certain propagation delay. So the speed of sequential circuit get affected. It reduces with an increase in the number of components, and the circuit complexity is also increases. So there is always the intention to reduce the number of states while implementing or designing the sequential state machine, and therefore the state reduction is an important aspect of designing a sequential machine, so that must be studied. We know the relationship between the number of states and number of state variable. That relationship is given in this equation. 2 raised to x is equals to y is the relation between number of state and number of state variables, where x represents the number of state variables and y represents the number of states. 2 raised to x is equals to y. If number of state variables are 2, suppose, then the number of possible states are 4. So as the number of state variable increases, the number of states in the state machine increases. So in uh, designing of sequential state machine, our intention is to reduce the number of state variables, so the number of states get reduced. That we have to study in next point. We can reduce the number of states. We may also reduce the number of state variables. That is, number of state variables are nothing but the number of flip-flops required to implement the sequential machine. So number of state variables represents the number of flip-flops required to implement the state machine. and as the number of flip-flops are reduced, the number of states get reduces, and to implement such a expression, having less number of terms requires less number of components, so the cost decreases, complexity reduces, and the speed of operation get enhanced. That are the advantages of using a state reduction in a sequential machine designing. Now, the state equivalence theorem. That theorem is used for identifying the redundant state or equivalent state is given here. The state equivalence theorem, two states SA and SB are equivalent if and only if for every possible input X sequence the outputs are same and the next states are equivalent. So what is the theorem states? The two states are equivalent if the outputs are same and next states are equivalent. That is the theorem. We will discuss the theorem in detail. Let n of Sx be the next state. This is the next state of present state S if input X is present. Means for input X and having the state S, n of S, n of Sx be the next state, and if output Ya is equals to output Yb, and if next state of A and next state of B are same, then SA is equals to SB according to the state equivalence theorem. Their outputs are same, that is Ya equals to Yb, and next states are equivalent, then the two state SA and SB are said to be equivalent. In short, the two states are equivalent when outputs are same, that is Ya equals to Yb. These are the outputs of state A and state B, and if they are equal, and n of Sax and n of Sbx are the next states of state A and B, and if they are equal, same, then the two states are said to be equivalent according to the state equivalence theorem that is given here. If states SA and SB occupies the same row of the state table, different rows of the state table, and if they are equivalent, if the states are equivalent, then one row can be eliminated from that state table. Means what? If this state occupies the two rows in the state table, and if they are equivalent, means they are redundant, one row in the state table is eliminated because there is no need to take both the rows or keep both the rows which are having same states or the states are equivalent, then one row has to be eliminated, so one row get removed from the state table. The properties of equivalent states, the three properties are listed here. The first is the symmetry. If state SA is equals to SB, then SB is equals to SA. If the first state is equivalent to second state, then second state must be equivalent to first state. This property is called the symmetry. Then The next is reflexivity. Each state is equivalent to itself, that is SA equals to SA or any state. Each state is equivalent to itself. That is what the reflexivity property of equivalent state. And the third is transitivity. If state SA is equivalent to state SB and state SB is equivalent to state SC, then state SA is equivalent to SC. That is, if first state is equivalent to second state and second is equivalent to third state, then the first state is equivalent to third state. These three are very important properties of equivalent states, and we have to use these properties in the reduction of equivalent states in the example to be studied next. Three properties: symmetry, reflexivity, and transitivity. Okay, the state reduction now. So there are two methods of state reduction. The first is equivalence classes method, and the second is implication chart method. So in this lecture, in this video, we have to study only the equivalence classes method of state reduction, and one example of equivalence class method of state reduction will be taken here. So let us go through it. What is the equivalence classes method of state reduction? What steps to be followed? These steps are given here. The equivalence class algorithm partitions a set of states into groups or classes based on the next state and output for a given input sequence. What is done here? The partition of the states into groups is done, and that is to be done on the basis of next state and output for a given input sequence. All those states which are having same next state and output are grouped under a common class, or they are grouped together. If group contains single state, no redundancy within that class has occurred. Means there is no such states which are having same output and next state. Means that state is a single state, means no redundancy within that class has occurred. That group is called, referred as class. Go on partitioning the groups as long as possible. Partition the groups if possible. The states within a group are said to be redundant and hence equivalent. The number of states which comes under the same group are said to be redundant and hence equivalent. So in that group, if there are two states, then those two states are said to be equivalent state, and we will replace that two state with a single state. Or if it contains more than two states, maybe 3 4, then instead of using all those 3 4 state, we'll represent that group with a single state. That is what the redundant state or the equivalent states are. So take only one state from that group and eliminates all rest of the states. That is what the equivalence classes method. What is to be done in the equivalence classes method. First, we have to partition the groups. Partition the group states into groups, and each group is set to be a class. The number of states in that group are set to be the equivalent state. We will represent that group with a single state. If there is only one state in the group, then there is no redundancy within that group or that class has occurred. The state within the group are redundant. So in that way, we can use the equivalence classes method of the state reduction. Let us see the example of equivalence class method of state reduction. See here, one state machine is described or presented in the state table for the present state. There are 5 states in the state machine: S0, S1, S2, S3, S4, S5, and the next state and output are given here. This is the next state or input x equals to 0 and z is the output. X is the input and z is the output, and x is equals to 1 and z. That is, when input x is equals to 0, the output of the state, and when input x is equals to 1, output of the machine. So if the present state is S0 and input x is 0, next state is S4 and output is 0. If the input is 1 and present state is S0, then the next state is S3 and output is 1. So in that way, the state table can be understood. Similarly, for rest of the state, for present state S1, when input x is 0, the next state is S5 and output z is 0. Similarly, when input x is 1, for state S1, the next state is S3 and output z is equals to 0. Here, for present state S2, when input x is equals to 0, the next state is S4 and output z is 0. Here, for state S2, when input x is equals to 1, next state is S1 and output z is 1. Here, for state S3, when input x is 0, the next state is S5 and output z is 0. And for input x is equals to 1, for state S3, the next state is S1 and output z is equals to 0. Similarly, here for state S4, when input x is equals to 0, next state is S2 and the output z is 0. Here, when input x is 1, next state is S5 and output z is 1. And for last state S5, when input x is 0, the next state is S1 and output is 0. And for input x is equals to 1, next state is S2 and output z is 0. So in this way, the state machine is described in the state table. Now we have to use equivalence class method of state reduction, that is of partitioning of the state, is to be done. So how it is done, let us see one by one. Consider this state table. Using the state equivalence class method, find the equivalent state. This is the problem at hand, and we have to find the equivalent states in this state table. So first step 1 is given here, that we have already described. Partition the states so that there both input and output values will be in the same class. Both the input and output values will be in the same class. Two classes occur when we do this. See here how the states are grouped. Why they are grouped, that we have to see. State S0, S2 and S4 are grouped because Z equals to 0 when x equals to 0 and Z is equals to 1 when x equals to 1. First of all, we have to concentrate on output column of the state. If their outputs are same, then we can group the states together. So very first thing to be done is that to focus on the output column of the state table. See here why these three states are grouped together: S0, S2 and S4. See the outputs. For input x equals to 0, see here output 0, 0 and 0. So the outputs are same, and similarly here 1 1 1. Here the output is different. If we consider S1 state, output is here 1 and here is 0, so we cannot take S1. Very first thing is to focus on the output column or the state which are having same output. So here for state S0, S2 and S4, the output under x equals to 0 is 0 0 0, and under x equals to 1 it is 1 1 1. So these states are grouped together. The next group is states S1, S3, S5 forms the next group. Since z equals to 0, they are grouped. Since z equals to 0 when x equals to 0, means for S1, S3 and S5, see the output column under x equals to 0, the outputs are 0 and z equals to 0 again, 0 0 0 when x equals to 1, means under x equals to 0 and x equals to 1 condition, these states output are same, so they are grouped together. So two groups are formed in this state table. One is containing states S0, S2, S4, and second group contains the states S1, S3 and S5. So let us name them as a C1 and C2. These two groups are said to be, this one is C1 and this one is C2, which is given here, and this partition is said to be one equivalent partition. C1 is S0, S2, S4 and C2 is S1, S3, S5. Okay, so let us represent it with a state table that will be given here. See this one, the equivalency next class table, table 2, we have discussed that C1 and C2, because their outputs are same, since C1 contain S0, S2 and S4, whatever the states in this column, they are to be represented as C1 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 or C2 C2 C2, means depending on the state table, that uh, class name are to be written in this next state column. Okay, here C1 is written because the state table here for S0 x equals to 0, the next state is S4, so S4 belongs to C1, therefore C1 has to be written here. Whatever the state S0, S2, S4 will be there, instead of these three state, we have to write C1 in the one equivalency next class table, and for state S1, S3 and S5 we shall write the C2. So S0, S2, S4 has to be replaced by C1 and S1, S3, S5 has to be replaced by C2. That is what given in this table. So S0, S2, S4 for input x equals to 0 becomes C1, 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 C2, 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 and for second group S1, S3, S5 it becomes C2, 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 C1. Okay, that description is given here. The next class table is constructed as shown in table 2 from table 1. It is constructed from table 1. Present state S0 has next state S4. S0 has next state S4. Here S4 is there, when which belongs to class C1. So C1 is written in here. So C1 is written in x equals to 0 next class column. State S0 has next state S3. Here it is S3. So SC2 is written in x equals to 1 next class column. That is what here C2 is written. Similarly, it is to be done for rest of the cases. State S0 has next state of S3 when x equals to 1. since S3 belongs to class 2, that is what written there, S0 C2 return in x equals to 1 next class table column next class column. So in this way the one equivalency next class table has to be filled. Now the next is to partition this one equivalency next class table further. If we observe it carefully, here for this group C1 all states are equal, but for this table, this group, this class C2, here C2 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 and here C2 C2 C1. So this state is having different class here. It is C1 and in rest of the point or places it is C2. So we can further partition the state table. Now step 2, two equivalency next class table. This partition determines two equivalency test each state within the classification found in step first. So we have to partition that state table further possible, and as we discussed here, since the states are this state is different, we have partitioned them like this. So they are now to be named as C11 here, C21 and C22, since all state having same next class, so they are written, they cannot be partitioned further here, so they are written like this: C11 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 C21 C21 C21. And what is C11 contains the state S0 S2 and S4 belongs to class C11. If S1 and S3 is there, it belongs to class C21, and C22 is having single state S5, so they are classified as C11 having 3 state S0 S2 S4, C21 having 2 state S1 and S3, and C22 having S5. So whenever there is S0 S2 and S4 in this column, this state, then we'll replace them by C11. If there is S1 or S3, we replace them by C21, and if there is S5, then we'll replace them by C22. So accordingly we have to make the entries in these columns. By considering the state table first, we can enter the values in this column. So it becomes, or it appears like this. That same thing is written here. Just go through it. Test C1 for each value of input x, we observe that for x equals to 0, next class is C1, and when x equals to 1, next class is C2 for all states contained in C1. This means no new partition of C1 is possible. That is clear from here. The test C2 for each value of input x, C2 has to be tested, this group. Here we observe that for x equals to 0, next class is C2, and for x equals to 1, C2 is the next class for state S1 and S3. But here C1 is the next class for S5. So the partition is done in this way. Therefore, two equivalent classifications given here: C11 S0 S2 S4, C21 S1 S3, and C22 S5. The new class table 3 is constructed from table 1 to show the two equivalence classification that is given here. Now we proceed for three equivalency classification. Step 3. Again try to partition that two equivalency next class table if possible. So if we observe the table carefully here, last one, here S0 and S2 states having same max states C11, C11, C21, C21, but S4 having C22 here. So the partition is possible here. So C11 will again partition. Next step, step 3. So observe it carefully. You will come to know how it is partitioned and how it is named. Now the groups are to be named as C11, C112. S0 and S2 is having same next state, so they are grouped like this: C112, C112, C211, C211. Whenever there is state S0 and S2, they are to be written in this way: C11. If state S4 is there, it is to be written as C112. If state S1, S3 is there, C211, and for S5 it is C221. Test C11 for each value of input x. Here partition can be done so that C11, that is S0, S2, and 112, S4. Test C21 in table 2. Be careful, that is this partition is done from the table 2, so that table must be referred here. Test C21 for each value of input x. No further partition is possible here. The C22 for each value of input x. No partition is required as it contains only one state. So after doing the complete partition, the classes are like this, which are here: S0 and S2, they come under same group and it is named as C111. S4 C112, S1 S3 they are belongs from C2111, and S5 from C221. Again, try to determine for equivalency or try to partition this state table. If we observe this state table carefully, if partitioning is further possible or not, see this first group C111 and observe the next state whether they are same or not. 112, 112, 211, 211 means here for x equals to 0 column the next states are same, and for x equals to 1 column next state are same. So this cannot be further partition. This contains the single state, so no partitioning is possible. Here C211, observe the next state. These two are same, C221, C221. So next partitioning is not possible. And again here 211, 211. So no further partitioning is possible. And since this is a single state, partition is not possible. So there is no further partitioning of this state table is possible, which is given here. No partitioning is possible. So states within the same class are said to be equivalent. That is C111 contains S0 and S2 means these two states are said to be equivalent states. That is S0 is equivalent to S2 and this C211 contains two states S1 and S3. So these two states are equivalent. So in this way we can get the equivalent states using the equivalence class method. Now once the redundant states are obtained, we have to draw the modified state table this way. See here, this is the state table given in the example, and as we have found state S0 and S2 are equivalent and S1 and S3 are equivalent. So for every state in the state table S2 has to be replaced by S0 since these two states are equivalent. So where we find the S2, we'll replace S2 by S0 and S3 by S1. So in this column S2 is here, replace it by S0 since they are equivalent. S3 replaced by S1. Here S2 is present here, so S2 is to be replaced by S0 and S3 is replaced by S1. So in this way the equivalent states are to be replaced with a single state, and once it is written, you can observe here these two rows S0, S0, next state is S4, S4, output is 0, 0, S1, S1, 1, 1. So there is no need to have these two rows simultaneously. These two row is replaced by a single row, that is S0, which is given in this simplified state table. And if we observe this S1 and S3 row, it contains same state S1, S1, S5, S5, 0, 0, S1, S1, 0, 0. So these two row are replaced by a single row in the state table is here S1, S5, 0, S1, 0, and rest of the state S4 and S5, since they are not equivalent containing single state, so they are to be kept intact. So it is S4 is having S0, 0, S5, 1, S0, 0, S5, 1, and S5, S this row S1, 0, S0, 0, S1, 0, S0, 0. So after finding the equivalent state using equivalence class method, the equivalent states are found and they are replaced with a single state, and a modified simplified state table is drawn or written here. So in this way, the equivalent states can be found using the equivalent state methods. In this simplified state table, states S2 and S3 are no longer exist in table 6. Here they are not present. We may rename the state. We can rename this state like S0 is A, S1 is B, S4 is C, and S5 is D, and we can rewrite this state table, rename the state, and write the new state table. Table 6 contains only 4 states. Now the main advantage of state reduction is that this state table contains only 4 states, and actually it was containing 6 states. To implement such a state machine having 4 state, 2 state variable. So to implement the 4 state machine, it requires the 2 state variables or the flip-flops compared to 6 state. Here 6 states requires 3 state variables, that is 3 flip-flops needed to realize the original sequential machine given in table 1. That is the advantage of state reduction in sequential machine. To summarize the equivalence class method, we come to know that using the equivalence class method, we partition the state into the classes which is having same output and next state. Go on partitioning the states till possible the states under the same group or same class are equivalent, as we found S0 and S2 they were under the same class, so these are equivalent and we replace them with a single state. Once we find the equivalent state, we replace them in the state table, and we can write the simplified state table as given in this table 6, and we can come to know that using the equivalence class method the equivalent states can be find out, and it is very simple to find the equivalent states using the equivalence class method. Once equivalent states are found, just prepare the simplified state table and we can draw the state diagram. So that is what the equivalence class method of state reduction. Thank you.